Good afternoon. Welcome to the last session of genomics and proteomics for today, and I believe for this week. And we are going to have a wonderful session for you, starting in just a moment or two. And our first speaker is Mahbub Latif, who is going to be talking with us about selection of two-color microarray designs using genetic algorithms. So, over to you.
Thank you. First of all, I want to say thanks to the organizers for giving me the chance to present my work here. And the title of the talk, Selection of Good Two-Color Microarray Design Using Genetic Algorithms. This is a joint work with Edgar Brunner of University of Göttingen and Frank Bretz of Novartis Pharma. Okay, so this is the outline of my talk. First I introduce the problem, the way I define. Then I will describe the model I use for defining design selection criteria. I define two criteria. One is optimality criteria, another is robustness criteria. Robustness not against the homoscedasticity. Here robustness against missing observations. And then I will describe a method for searching good microarray design. What is good? Good means is optimum and it's robust. Okay. So by design of microarray experiments, I mean allocation of competing mRNA samples to the arrays. And in allocating competing mRNA samples to the arrays, one need to decide which pair of sample, which I will call treatment, which pair of treatments should be hybridized on a single array, and what would be their ideal die-level protocol. And by good microarray design, we mean like a design which can estimate the effect of interest with high precision, and it is robust against missing observations. So with in the presence of missing observation, the design will not break down. And in practice, before conducting a microarray experiment, what we know, the experimenter knows the number of competing samples. So what he wants to compare, and also he knows the number of arrays he wants to use in the experiment. And of course, he knows the research questions of interest. Now the problem is what is the ideal way or good way to allocate the k samples into n arrays. So beforehand, k and n are fixed, and also the research question. So we use a gene-specific model for background corrected normalized log intensities. The model contains the main effect of array, die, and treatment. And we include the die effects in our model because some of recent papers mention that usual normalization procedure cannot adjust gene-specific die effect. It can adjust only overall die effect. And here our main goal is to estimate the treatment effect. Die and array effect act as an block factor. We assume the treatment k and k prime are hybridized on array I, and k is labeled with die j and k prime with j prime, and j die is the difference of log intensities between treatment k and k prime. That means between die j and j prime, in other words between green and red die. And j die indicates the measure of gene expression from array I. If zi greater than 0, one can say, okay, that gene is more expressed in treatment K than in treatment K prime. And we assume the homoscedastic error. This model we can write in matrix notation as in equation 1, where Z is a vector of n elements, each Z1, Z2, Zn, each Z values come from one array. And the parameter vector beta contains both the parameters corresponding to the dye effect and treatment effect. And X is the design matrix, and what is the form of the X. Here is one design which has 4 arrays. Each arrow represents an array, also says about their dye level protocol. Say for 1 to 2 correspondence an array, 1 to 2 correspondence an array where treatment 1 and 2 are hybridized, and treatment 1 is labeled with say green dye and treatment 2 with red dye. So we follow this notation. And corresponding to this design, the design matrix would be like this. Say for this array 1 to 2 corresponds to first row of the design matrix, and this array 2 to 3 correspond to the second row of the design matrix, and so on. Different experiments may have different research questions. For example, in pairwise treatment comparisons, one may, for example, in simple experiment, one may interest in pairwise treatment comparisons, and in multifactor factorial experiment, one may interested in main effect or interactions, and all these research question can be expressed in terms of the regression parameter beta. For example, for pairwise, you can write the contrast vector in such a way that we can compare treatment 1 and treatment 2. Since in our design, in our model, we included both dye effect, and we know that dye and treatment effect are confounded in an array. So estimability is an issue here. So what is estimability? So estimability of a function is defined in a way like, if there is any linear combination of the response, if there exists any linear combination of the response which can be used to estimate the effect of interest without any bias, then that effect of interest is estimable. So a effect of interest C transpose beta is estimable. A necessary and sufficient condition is it should satisfy equation 2. If the effect of interest is estimable, then usual least square theory can be used to estimate it, and the corresponding variance expression has 2 parts. The first part, C transpose X, G inverse of X transpose X and C, this is called variance factor, and the known sigma square. So our goal is to minimize this variance, and note that here the variance factor is a function of research question C and the design. So research question is fixed beforehand, so we can play with design to make this variance factor smaller. So we want to find a design which makes this variance factor smaller. So as a function of this variance factor, we define some one optimality criterion. So this is actually is taken from a published paper which Professor Mukherjee shows, Landgrave and Brunner et al. It was published in 2006 in CSDA. So I use the same optimality criterion, and according to this definition of E optimality criterion, if value of psi, large value of psi indicates more optimum design. And if you have more than one research question, say here you have C1 and CQ, you have Q research questions, then the average of these things can be considered as a optimality criterion. Or if you want to give more importance to one question than other, one can use the weighted average too as an optimality criterion. Okay. In practice, in microarray data often contains missing observations due to some crashes or dust on the array. So you may get no data point for a specific gene from one or more array. So we want to, and the missing observation, the missing observation may cause a breakdown of the analysis. You may not estimate the parameter of interest, or it may reduce the precision of the estimates. So we try to define two robustness criteria which will quantify a design's characteristics against the missing observations. So the robustness criteria we have defined are based on residual design. What is residual design? So residual design is the possible design that can be constructed with a specific number of missing arrays. For example, if we have a design with 4 arrays, so then we could have 4 residual design with 1 missing array. So these are, each of these are residual design. And to fix the notation, I defined R sub m of a matrix Xn is a set of residual design, set of design matrices corresponding to the residual design with m missing arrays. So all possible design matrices one can construct with m missing arrays. And R sub m star is a subset of this R sub m. It only includes those design matrices for which the effect of interest is estimable. So this is the large set, and this is subset of this. Or if all these residual design can estimate the effect of interest, then these two sets are similar. So the first robustness criteria I define is breakdown number, which is the minimum number of missing observations that lead to at least one residual design for which the effect of interest is not estimable anymore. So if we check all the residual design and find one cannot estimate the effect of interest, then the number of missing observations for which those residual designs are constructed is the breakdown number. So large breakdown number is good for design. And the second one is just the average of E optimality criterion over the residual designs. So this is average optimality criterion. So how to use these two criterion in selecting good design? So here I have 3 competing designs for comparing 4 treatments, 1, 2, 3, and 4. I denoted by D1, D2, and D3. And by using the optimality criterion, I can get the E optimality value 2 for D1, for D2 is 5.33, and D3 is 5.33. So I can say D2 and D3 more optimum compared to D1 for estimating the effect of estimating the effect C transpose beta, in this case comparing treatment 1 and 2. So which design should we use between these two? Okay, in terms of efficiency, we can use any of them, but if we think there is a possibility of missing observation. So we can write down the breakdown number for these two design, and it may give more information that the last design D3's breakdown number is 4, and whereas the D2's breakdown number is 2. So we can that using D3 in the experiment is better than using D2 because D3 is more robust. So robustness is extra characteristic which one can use to select design when you have several designs which are equally efficient. Okay. Before I describe how to select a design from a three competing designs, but in practice one can get thousands of designs and you have to find the best one. So here I consider an example. So suppose I have Q questions, so research question Q research questions, and I have K treatments. So in total I could have n number of possible arrays, and total number of, and I know I am interested in small n number of designs, small designs with small n arrays. So possible number of designs with small n arrays could be T, and I defined a set A's which is the set of design matrices corresponding these T designs. Okay, and then this is my optimization problem. So this is my criteria, and I try to optimize it over all design matrices, all possible design matrices, and subject to condition that that design must estimable corresponding to all the effects I am interested in. So this is constrained optimization problem, and this is not easy to optimize. I tried to do a complete search, it didn't work, and search space is discrete, so I cannot use those method like Newton Raphson and other things. And here I will try to use a in design context I try a exact design instead of continuous design, which Professor Mukherjee talked in the last presentation. Okay, so to find the exact design, and I know the complete search is not computationally feasible, so I tried one which is genetic algorithm. I try to use genetic algorithm to find the best design. So genetic algorithm is a stochastic search process which mimics some important features of natural evolution to find at least near optimum design, near optimum solution of a optimization problem. The important features which are used as operators of genetic algorithms are selection, inheritance, and variability. Genetic algorithm usually used a chromosome-like data structure, and each element of the chromosome is called gene. So it's not the real definition of gene. Here you have a data structure and different elements it has, and data structure chromosome elements are gene. And to quantify the quality of your chromosomes, the function they use is called fitness function. So now I can define those elements of genetic algorithm from design from my problem. So in my problem, design is the chromosome, elements of design is array, which is gene, and the fitness is E optimality criterion. Okay, and this is a pseudo code of genetic algorithm. Initially, it will start with a initial population, then I find then I evaluate each of the designs, and I know which one is good, which one I rank them, and I select them for parent population. And from each pair of parent population, I combine them, which is called crossover, and then I get the offspring population, and some of the offspring population I add some variability, which is called mutation, and we continue this procedure until it converts. And in good, this is not this type of picture you will not get every time, but I saved it a good one. So this is like over generation. Usually, it should be the average fitness will increase. Average fitness means all the population, all the individuals in the populations. So now I'll show one example of genetic algorithm. So I consider a experiment, 3×2 factorial experiment, where 2 factors. One factor has 3 levels, and second factor has 2 levels. So total number of treatments has 6, and number of possible arrays is 30. And I tried different combination of main effect and interaction. And here I only show the situation where all the main effects, 2 main effects and interaction are of equal interest. One can use the other. These are the designs with 6 arrays, 15 arrays, and 18 arrays. And I have not tried to find good design more than 18 arrays. So, and it does not take that long. It's not like a one day. It's like 2 to 3 hours for 18 arrays, at least in this setup. And I also try to check like how robust are these. And I found, I use another design. The design with 12 arrays, the main effects is breakdown number corresponding to main effects is 3, whereas interaction effects is 4. And design with 18 arrays, the breakdown numbers are 6 for all effects. So this is just a result. And now, as I don't know any design, any paper which discuss this specific design, so I could not compare. But I know from Carr's and Churchill paper, like the best design for comparing treatment, 6 treatment and 8 treatments with this number of arrays, like with 6 arrays, 8 arrays, and 12 arrays, they define like this, with k arrays, k plus 2 arrays, and twice k arrays. And I did a simulation, 500 simulation, and I found this is the e-optimality value of the best design, and I found it's like almost more than 95% times the algorithm can get the design. And I also did something, I tried to regenerate the design I got, and most of the time I get more than 95% time I get the design which I got before. And another thing here is the average number of generations. It's not large, only 290. In genetic algorithm in other field, they usually do like 10,000 generations. So if I could run more, it's I guess we will get better designs. So in any cases I run more than thousands generations. So number of generations is very within 1,000. Okay. So here is the summary. We defined 2 robustness criteria which may be useful in some situation in design, good design selection, and GAB genetic algorithm based procedure is good, and it find at least known designs very well, and other design criteria can be used instead of e-optimality criteria. Okay, thank you.
We've got a few minutes for questions. So.
Yes.
Could you go back to the criteria that you're optimizing, to the constraint and the objective function? Yeah. How long does it take to compute the first thing you're maximizing and to check the criterion for each design? That's what is the, how hard is that computationally for each one of them? Say somebody plops down a particular X and you want to check that.
Yeah. for this example, I say it doesn't take more than 2 hours.
No, for one
Oh, I
value,
see.
single design.
Oh, I have not tried that.
I mean, as it goes through all the designs, the question is,
Oh, it's
you said you can't do it by complete enumeration.
yes.
There's too many of them.
Yeah.
How many are there?
Oh, it comes from this. It's million. It could be million. Like I tried only with 6 treatments, and I waited 3 days. It didn't come out.
Okay, so it's not even in the ballpark.
No.
So the question is, what kind of platform are you computing on?
Okay, I tried it in 2005 in, I don't know, it's a Linux machine and it's a good university, so they must have
You can't tell us the
No, I
size
don't
of the machinery.
no, I don't can.
And did you use distributed computing at all?
Sorry,
Did you use distributed computing
No.
like Condor or something?
no.
I'm just wondering if kind of crude devices like getting a bigger, smarter machine or using a network might help
Yeah.
things before you become elegant and genetic.
At first, when I get this optimization program, I thought I can write it. I wrote in C, so C is faster. And then I stuck, like it didn't work. Then I tried to find something else to finish my job. So just one way to avoid this complete innovation. Yes.
You built in robustness against missing slides by looking what happens if you really put one or two or whatever number of slides off. Another idea might be that you allocate in an initial design just, let's say, 50 or 75% of all the slides, then perform the experiment, look what happens, and then try to compute an optimum follow-up number of follow-up design using the remaining budget of slides.
But how do you know, like there are different way you can get the missing, you have different number of ways you can get the missing values, right?
Well, yes,
missing slides.
if you have 40 slides, for example,
Yeah.
you'll make an experiment with 30 slides.
Yes.
Perhaps there will be some missing slides then.
Yeah.
And given the realized design of 30 minus some numbers of slides, you can allocate an additional 10 slides to the experiment because you have a budget of 40 slides.
I'm not thinking this, but usually they don't. Usually, like in biology, at the beginning, they don't think about the missing. Like that is not a very important issue. But when you are going to the analysis, there is an important issue. So what I suggest here, just if you don't need to do much, just you have some competing design. From those design, which one is more robust? So just suggest
Yeah,
that
that's a
one.
good idea, but
Yeah.
this
So-
would be an alternative.
Yeah, thank you.
But then for to suggest you would have to keep the conditions identical.
Yeah,
The first set.
probably you have to include some blocking, additional blocking effect of the remaining number of slides.
Yes.
Your criterion is a combination of, it looks to me like C-optimal criterion, but you mentioned E-optimality. So
Okay, I just says I define my optimality criteria this way, and the paper I mentioned, they called it optimality. Yes.
You said that the A-optimal designs for K treatments in 2K slides are all known?
Yes. The paper from not all, for some specific number.
I'm going to say because
yeah,
I think
yeah.
it falls apart when
Yeah.
K gets large.
Yeah, not up to 15, I guess. So that's why I choose 10, which is for every combination, which is true.
Maybe one more?
GAs are quite sensitive to tuning parameters, things like
Yes.
before the crossover
Yes,
and the
yes.
mutation. Did you
Yeah.
have to investigate that?
Yeah. I did some simulation to choose which crossover value would be the best one. Even I tried different crossover protocols, and I found for my case about 7.75 is a very good number, and for mutation is 0.06 or something. But I did some simulation, I found which one.
Let's thank Mahbub again.